Okay, welcome back. This is now 2.4. We're dealing with continuity and one-sided limits. So what is continuity? Well, you can think of it as being able to draw something without picking up your pen. Okay. We'll now have kind of a more strict definition of it, and you can think of it in terms of a limit. So limits we only care about approach, but with continuity we care about approach and then what happens exactly at that point. So we'll define this thing kind of in terms of limits, and a very simple way of thinking of this with regards to limits is that if you could do one of those substitution limits, like if you're given the limit of 2x squared plus 1, and you could evaluate it via doing a substitution. For instance, for any value c, I could put c into here, and that will sort of give me the answer, quote unquote. Then this thing here is continuous. Okay, so that's, I guess, the sort of a way of thinking of continuity that we want to introduce here. And the way the book will introduce it is via these three criteria. Okay. And the first, I think the third criteria is the most important, but the first two, for continuity at some point, I guess we'll call it C. First, we require that the function is actually defined at C. So f of C is defined. Then we need to ensure that the limit exists at this point. So the limit of f of x as x approaches C exists. Okay. And the third one, the one that really says it all, basically the limit as x approaches C of f of x has to equal f of C. And that's what I mean by if you could do sort of a substitution on your limit, that thing is going to be continuous. So polynomials, we were able to do that. Those are continuous. Rational functions are continuous everywhere where their denominator does not equal 0. Sine is continuous everywhere. Cosine is continuous everywhere. The exponential function, e to the x, is continuous everywhere. So anytime you can take a limit and just do it via a substitution, that thing is continuous. Okay. Okay. So for continuity on a closed interval, it just needs to obey these rules for every point in that interval. Okay. So continuity on an open interval just means the function is continuous at every point in that interval. Okay. Okay, so we are given some examples of discontinuity in the book. This is from figure 2.25. I added one example to it. It's basically just kind of showing you some examples where these things fail, and you can see visually that they're not going to be continuous. Essentially, you can't draw them without picking up your pen. There's other sort of details. Sometimes it'll have a discontinuity which is fixable, and those will be called removable discontinuities. Okay, so let's take a look here. The first one is where f of x is not defined. Okay, so essentially there's a hole in your graph. So we're on some open interval from a to b. And then here's our graph. And then inside this interval, maybe at some point C, the thing just isn't defined. Okay, so in this case, it's not continuous on the open intervals. And literally, if you tried to draw it, you'd have to pick up your pen at that point. Okay. In this case, it's considered to be removable because you could define f of x to equal this, or f of x at c to equal this particular y value. Okay, so it's considered removable or fixable if you'd rather. Removable. Okay, the second case is when the limit doesn't exist, and this is a bad case because it's not even fixable. It's kind of like that. You've seen that that picture online of those people building that bridge, and the bridge's ends don't match up. It's that scenario. So here at C, the thing is defined, but it's defined up here, but you have to kind of do a jump to get from here to here. Okay, and it's called a jump discontinuity in some books. I don't think our book makes a big deal out of it, but the deal is the limit of f of c is not defined. It has two different limits in these directions. Okay, does not exist. Yes, and it's non-removable. You just can't define f of c to be some point such that these two directions would connect. So it's called non-removable. Okay, our third case then is one where the limit, this third case, will kind of fall apart. So the function will be defined, the limit will exist, but the limit will not equal the function at c. So it'll look something like this. So you have a hole in the graph, and then at c, at this value c, we've defined the function to be somewhere other than its limit. So in other words, the limit of f of c does not actually equal f of, the limit of f of x, sorry, does not actually equal f of c. Okay, so in this case, it is fixable. You just redefine your y value to be here, your f of c value to be here. So we'll call that removable again, a removable discontinuity. The last case, which isn't given in the book, is when you have some sort of asymptote, and in that case, f of c won't be defined, and the limit of f of c will not exist. So let's say you have a here, and then b here, and then at c, the graph maybe is shooting off to infinity, something like this, from both directions. Okay. So the limit, f of c is not defined. You could try to define it to be some value, but it's just not going to pan out. F of c is not defined. The limit of f of c does not exist. And the type is non-removable. There's no way of fixing this problem here, just doing some redefinition. Okay, so let's take a look at maybe some examples from the book. So 43, what are they looking for? They're looking for you to identify the discontinuities and then tell if they're removable or not. So we have f of x equaling x all over x squared minus x. Okay. So you're going to have discontinuities where the denominator is equal to 0. So you take the denominator and set it equal to 0. And we have x times x minus 1 equals 0. And so x is 0 or x is 1 are the discontinuities. Okay. Then we have to figure out if they are removable or not. So if you plug one in and it's a 0 over 0, so an indeterminate form with these rational functions, it's going to be considered removable. Okay, and so what am I saying? If you could rewrite it as I'm doing right here, and then just kind of remove it, it's considered a removable discontinuity. So this guy is considered removable. And then this other guy where you have the asymptote is non-removable. So we have an asymptote there. You can redefine the function then. So you could say f of x is equal to this piecewise function, x all over x squared minus x, if x is not equal to 1. And then, sorry, if x is not equal to 0, and then -1 if x is equal to 0. Okay, and that will fix it. Okay, so note, if you put x equals 0 into here, you get 1 over -1, which is -1. But if you put it over here, you got trouble. You got trouble, right? It would be -1 over 1. So sorry. If you put 0 into here, you get 0 over 0, which is our indeterminate form. And this would be the fix. This would basically remove the discontinuity. Okay, let's one more. So 49, f of x equals x all over x squared plus 1. This one's actually continuous everywhere. The denominator is never equal to 0, x squared plus 1. If you tried to set it equal to 0, you see x squared equals -1. X squared is always greater than or equal to 0. So there's no way x squared can be -1. And that was the only potential place where this guy would fail. So this guy is continuous everywhere. Okay. All right. One-sided limits. So in certain circumstances, I mean, we've kind of already looked at this prior to this section, when we dealt with limits that failed to exist. And the example we looked at was this example of a piecewise function that's -1 when x is less than 0, and then +1 when x is greater than or equal to 0. Okay. So in one direction, if I come in from the negatives, the y value will always be -1. Okay, so in other words, the limit of f of x as x comes from the negative direction, and that's how we symbolize the direction of approach, f of x will always be -1. Okay. Then from the other side, when x is greater than 0, the y value is always 1. So the limit as x approaches 0 from the right of f of x will always be +1. Okay. Now the limit of f of x as x approaches just plain old 0 does not exist. Right? So f of x, this does not exist because we have different left and right hand limits. Okay? But we can, in fact, just figure out the left and right limits. That's legal. You can do that. It's just when you put it all together and say, what's the limit as we approach from both directions? In this case, it's not the same in both directions, so we have to say the limit does not exist. Okay, so if you say that this does have a limit, what the implication is that these guys equal each other. Okay. All right. So, anyways, maybe running out of paper. Let's take a look at some of the problems from the book. So we have number 11 here. What is it? So it's the limit as x approaches -3 from the left of x all over the square root of x squared minus 9. Okay. So I'm just checking to make sure I got enough paper. So I'm going to need more paper. Okay, hold on one second. Over here. Okay, we should be good now. Okay, so we're approaching -3 from the left. So on the number line, here's -3, and we're coming in from this direction. Okay. Note from the other direction, if I tried to move in, oh wait, yeah, we're good. If I try to move in from this other direction, I'd be thinking of numbers like -2 in the approach. And if you put -2 into this radical, you'd have a huge issue. So there's no way you could take the limit from this direction because it wouldn't be defined. Okay, this expression would not be defined. So we can take the limit in this direction. That's what we're after. So you can do a table of values if you want to. So x, y, and then you know, you're looking at -3.1 and then -3.01, etc. Let's just put a bigger one in there. If you put those in your calculator, and I've already done this, you get -3.97, -12.98, -122.48. What's going on here is you have unbounded behavior. You can put a name on this type of behavior. It's going to -infinity. It just keeps going down and down and down as we get really close to -3. In fact, we should have some, I presume, some sort of asymptote at that point. So this will be -infinity. So if it has some kind of unbounded behavior, you want to label that type of non-existence. So technically, you could write DNE, it does not exist, but here we want to describe that kind of behavior and put a label on it. And that's what I'm doing here, is -infinity. Let's look at another piecewise guy. So number 17, we have f of x equaling x plus 2 over 2. And then 12 minus 2x all over 3. And then this is when x is less than or equal to 3, and this is when x is greater than 3. Okay, so I believe we want to consider the limit as x goes to 3 from the left of this thing. So you're thinking of, and maybe you need to draw a little number line, 2, 2.1, 2.2, 2.9, 2.99, 2. So you're thinking of x values less than or equal to 3. In other words, you're always using this expression. And so as we approach 3 from the left, we could do a plug and chug here into this expression. And you have 3 plus 2 is 5 all over 2. Okay. So if you come in from the other direction, you're going to just be using this guy. And you could do a plug and chug in that direction. Let's see. The limit as x goes to 3 from the right, then of f of x, is just plugging 3 in here. 12 minus 6 is 6, all over 3 is 2. So note, in this case, you would have a discontinuity when x equals 3 because you can't, the limit of the function is not equal to the actual function's value at 3. In particular, its limit does not exist, right, at 3. And that was the second criteria for continuity. The limit as x approaches 3 of f of x, well, from one direction it's 5/2, from the other direction it's 2, so therefore it fails to have a limit, and we would say it does not exist. In other words, it's discontinuous at x equals 3. Okay. Let's carry on, look at 27. So here we're looking at limit as x goes to 3 from the right of the natural log of x minus 3. If you remember what the natural log looks like, the natural log of x is just this guy, And then this is a shifted version. Of course, when you shift the natural log, you have to move its asymptote over at the same time. So I'm going to move over to there. And of course, our shifted version looks like this. So as x goes to 3 from the right, the y values are going down, 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 right, to negative infinity. So the limit does not exist. It's not continuous there. And we'll describe that limit then as negative infinity. Okay. Continuity on a closed interval, then we'll sort of use this idea of limits from left and right and say that if we want to consider the continuity on a closed interval, you check to see if the limit going from this direction, limit going from this direction, actually are substitution type limits. Anyways, let's take a look at the criteria that are going to be given here. So section 3, we have continuity on a closed interval. Okay. So first, you know, what interval A to B, and we want to make sure that all of the points inside this interval have limits to, you know, limit as x approaches c of f of x equals f of c for all c values in the open interval from A to B, open interval. And then for the endpoints, we want these one-sided limits to be in operation. So we want the limit as x approaches A from the right of f of x to equal f of A. And then we want, thirdly, the limit as x approaches B from the left of f of x to equal f of B. Okay. So we kind of have this idea of right-handed continuity and left-handed continuity. Continuity from the left, continuity from the right. Okay, so let's look at 35, and we have f of x equaling 3 minus x, and then 3 plus 1/2 x. And it's 3 minus x if x is less than or equal to 0, 3 plus 1/2 x if x is greater than 0, and we're on the interval from -1 to 4. Okay. First, I'm going to check these two second criteria. All right, so the limit as x approaches -1 from this direction, from the positives, from the right, the input values we're going to be using then were less than 0 as we get really close to -1 from the right. We're using this expression. So is it a plug and chug is kind of what you're asking. And yeah, it certainly is. It's a polynomial, so you could just plug it in and you get 3 minus -1, in other words 4. Okay, so that number 2 works. Number 3, then we have to check the limit as x approaches 4 from the left. Okay. As we get close to 4 from the left, x is greater than 0, so we'll be using this portion of the function, 3 plus 1/2 x. And then, of course, this is polynomial. We can go ahead and directly substitute and get 3 plus 2, in other words, 5. So yeah, the two limits are going to work for us in those directions. This is just f of -1. This is just f of 4, which is what we desired. Okay. For all the points in AB, this is a little harder. There's, for the most part, there's no issue for values that are not equal to 0. Okay, it'll just either be this function or this function. They're both polynomials, therefore you can do substitutions. The troublemaker is at 0, so there's a question as to whether or not, so this is actually related to criteria 1, but there's a question of whether or not we have a limit from the same, if the limit from the different directions are equal to the same thing at 0. So in other words, I need to verify that the limit as x goes to 0 from the right is the same thing as the limit as x goes to 0 from the left. Okay, and if those guys are the same, then it'll be continuous because I think it's Theorem 2.10. Okay, so let's look at it. If the limit as x goes to 0, so when I'm coming in from the right, I have values that are less than 0. I use this, so that'll be 3. And if I'm coming in, sorry, this was coming in, yeah, from the right. If I'm coming in, oops, so this should have been the other way around, right? So this should be the limit as x goes to 0 from the right. I'm actually using this guy because the x values are greater than 0 from the right. Right? So here's 0. I'm coming in from this direction, so it would be positive values. So I'm using this piece. Okay, so it's 3 plus 1/2 x. If I plug 0 in there, I just get 3. When I'm coming in from the left, I'm using the other piece, 3 minus x, and again, I just get 0. So, oh, sorry, 3. 3 minus 0 is 3. So these guys are the same, and so it's going to be continuous at x equals 0. Let me just make sure. It seems like that's a criteria for limits being good. Make sure. Yeah, so that's a criteria for limits. The limit existing. Sorry, so this doesn't necessarily imply that the function is continuous at 0, but because 3 is f of 0, then yeah, now I can conclusively say it is continuous. The fact that the limits are the same just means that the limit exists at that particular point. It doesn't mean that. I mean, even then, it seems like it's not entirely clear, because you could have situations where certainly this guy comes down to here, and then maybe the other guy is going towards some other point, and then no, it seems like it would be forced to have a limit if the two values were the same, because this limit would be then different than this limit. Anyways, this the fact that the limits are the same implies that the limit exists. So you could go through the criteria, if nothing else. This says, well, f of 0 is definitely defined. Secondly, the limit exists. It's 3. And then thirdly, does the limit of f of x equal f of 0, right? And f of 0, if you plug 0 into this piecewise function, it's going to go into here, and it will be 3. So yeah, it's got to be continuous. Okay. So hopefully I didn't butcher that too much. But yeah, when you get confused, you kind of have to default to your original definitions and then go through the criteria. Okay. Anyways, I think I'll do a little better in class on that one. Let's take a look at properties of continuous functions. So certain things are true for sums and differences of continuous functions. Those results will also be continuous. Okay, so it's like properties of continuous functions. So to make this easier, let's just take some continuous functions. F of x equals e to the x is continuous everywhere. And g of x equaling x squared is also continuous everywhere. Okay, so if that's true, a constant times a continuous function, or either one of these, will also be continuous. So let's say h of x equaling 5 e to the x is continuous everywhere. So I'm just kind of trying to amend this so I don't have to rewrite is continuous every time. The following are also continuous. So first this guy, let's call this h1. h2 of x equaling e to the x plus x squared. That guy is going to be continuous. Products will be continuous. Okay, so there's no mystery there. So if you have x squared e to the x, this will also be continuous. Fourthly, x to the fourth of x equaling e to the x all over x squared. That'll be continuous everywhere except where the denominators equal to 0. So we'll say maybe something like x cannot be 0. And you can also worry about composition functions. So step 5, f of g of x is continuous everywhere as well. Okay? And sometimes there's going to be issues here. So maybe this internal function won't be continuous at a certain point, but the outer part will be. So we want to just maybe take a look at something weird like that. So 78, we have f of x equals 1 all over x, and then g of x equals x plus 1. So we know this guy is not continuous at x equals 0. Okay. F of x just isn't defined there, so it won't work. This guy is continuous everywhere, though. Let's now consider the composition of f of g of x and see where it's continuous or discontinuous. So if I plug this into here, I get 1 all over x plus 1. And then this guy turns out to be continuous, right? So that's kind of a continuous at x equals 0. The real issue now is when x is negative 1. So doing a composition can change where the discontinuity is. So we're basically requiring f to be defined at g of whatever point, not just f being defined at this particular point. So we need f to be defined wherever g of whatever is. Okay, so it's in this case we need the particular negative 1 that we put in here. We need f to be defined at g of negative 1. Okay, in this case, that's where we're working with. We're not like looking at this. Okay. Anyways, the last section is the intermediate value theorem. So we have section 5, intermediate value theorem. And this is a weird existence theorem. It's theorem 2.13 from the book. Visually, you can kind of think of it as if you have some kind of function continuous on a closed interval this time. And so we have a function maybe going from here to here. So this would be f of a, and this point up here is f of b. For any point in between f of a and f of b, there will exist a c value such that f of x will go through that point so long as f of x is continuous. Okay, so for example, if I'm going from f of a to f of b, and there's this k value in between them, it will definitely have to cut through this k value in order to get there. In particular, there'll be a value c such that f of c is equal to this k. It's a silly thing, but it's important nonetheless. So let's look at some example, maybe 103. We'll say like 103, and we're given f of x equals x cubed plus x minus 1, and we're dealing with some interval from 0 to 5. We want to know if there's any zeros in that interval. Okay, so depending on how long it's been since you took pre-calc, you may not know how to get a 0 out of this thing. And the intermediate value theorem is saying that so long as your function is continuous on this closed interval, you can kind of, if you can pick out values around 0, then it forces this thing to have a 0. So in other words, let's look at f of 0. And what does that equal? Well, that equals 0 plus 0 minus 1 is minus 1. And then let's look at f of 5. So that equals 125 plus 5 is 130, minus 1 is 129. So visually, the graph of the thing is going from, at 0, it's down at -1. Okay? And then at 1, 2, 3, 4, 5, it goes way up to 129. So whatever the function's doing, it must, because it's continuous, go through the x-axis in between 0 and 5. Sorry, you couldn't see all that junk, all that good stuff. So if at 0, it's below the x-axis, and at 5, it's above the x-axis, there must be some c value in between 0 and 5 where it crossed through the x-axis, and it's right there. We must have a place where f of something equals 0. Okay, so by the intermediate value theorem, there exists a value c in the interval from 0 to 5 such that f of c is equal to 0. Okay? So it's just an existence theorem. It doesn't actually tell us how to find that thing. But, you know, there it is. Okay, so it requires continuity. F of x must be continuous. F of a does not equal f of b. And this k value is in between f of a and f of b. Okay, so you see the book for the nice strict definition. This is just my synopsis. Okay, thanks.